Okay, here is the second security property of a hash function. It is closely related to one-wayness, and I think when a lot of people see them for the first time, they think they're the same thing, but there's a very subtle difference, and hopefully by thinking about the game, we can tease out what the difference is. So, the challenge, to read it out loud first, is a little bit different from the one before. So in the one-way challenge, remember how I turned around and I gave you an output and I said, you need to match my output. So I turned around, I gave you the output, I said it was 42, and you had to match the number 42. By contrast, in the collision resistance challenge, I don't give you any output. So it's still a challenge that you have to solve, but the challenge doesn't involve me giving you an output. That's the key difference between these two challenges. In the one-way challenge, I turned around, I hashed something, and I gave you an output that you had to match. In the collision resistance challenge, there is no matching involved. All that happens is I tell you, your challenge is to find any two inputs that have the same output. That's all that I care about. If you can find two inputs that hash to the same output, you win, and the scheme is not collision resistant. So the key difference between these two properties is that one-wayness of a hash requires you to match my chosen output. Collision resistance doesn't require you to match my output. You can pick any two inputs you want as long as they match and have a corresponding matching output hash. And your two inputs have to be different. No choosing the same input twice. That's cheating. So more formally, the thing that you have found if you solve this challenge is something called a collision. You've found two different inputs that have the same output. So you have two inputs, x and x prime. They are different, but their hash outputs are the same. So one question you might ask is, can you have a hash function with no collisions at all? Is it possible that every input maps to a different output, sort of like our block ciphers? Well, to think about whether that can happen, think about the number of inputs of the hash function and the number of outputs. The input is arbitrary length. It could be 1 byte, it could be 1,000 bytes. So how many possible input strings are there? Like infinity. There's as many as you can think of because you can pass in any length input string into the hash function and it's supported. How many output values are there for the hash function? 2 to the n. If it's an n-bit output, say 128 bits, you only have 2 to the 128 possible outputs. 2 to the 128 is a big number of outputs, but it is not infinity. So if you have infinity inputs and 2 to the 128 outputs, there's going to be at least some inputs that map to the same output. If you've taken a class like CS70 and you've heard about the pigeonhole principle, that's the principle we're using here. And if not, you can just think of it like there are more inputs than outputs, so at least some of the inputs have to be mapped to outputs. So what that means is collisions do exist, so the challenge should more formally say, not that it's impossible to find a collision, but that it's very hard for an attacker to find a collision. So to amend the challenge one more time to account for the fact that collisions, they're out there, but they're hard to find, the challenge really reads like this. If I tell you to find me a collision, two different inputs with the same output hash, we know that they exist. There's a bunch of them out there, but it is very hard for you to find it. And if you use a definition similar to the INDCPA one, you could say any attacker that runs in polynomial time has no hope of finding such a collision. They would have to run algorithms that take the length of the universe to find such a collision. So collision resistance really says it's computationally infeasible. It's not impossible. Someone with infinite time could come up with one because they exist, but it's computationally infeasible. Attackers with polynomial time have no hope of finding such a collision. So that's the intuition for collision resistance. And I guess taking the idea of collisions back here really briefly, this also needs to be defined in terms of computationally infeasible. So again, it's possible to find a different value that hashes to the same output if you have infinite time, but for attackers with polynomial time, if this is really hard, then we say that the scheme is one way. So both one-wayness and collision resistance are defined in terms of being computationally very hard, even though they are hypothetically possible. Nobody with any reasonable amount of time will ever solve these challenges if your hash is secure. Okay, one final thing about collision resistance, in case you're wondering how hard it is, you can go and look up something called the birthday paradox or the birthday attack. We won't talk about it in too much detail in this class because it's a little bit mathy, but if you're wondering how hard it is to find the collision, it's roughly exponential time. So this is why we said that polynomial time attackers cannot achieve finding a collision. It's because if you want to find a collision on an n-bit output, you usually have to try roughly 2 to the n over 2 tries. Where the n over 2 comes from, we won't talk about here. You can look up the birthday paradox. But the key thing here is that this is polynomial, or it's not polynomial, it's exponential. If this said like n squared or something, it would be pretty easy to find a collision. But because it says 2 to the n, we know that this algorithm would take exponential time. And if you had, for example, a 256-bit output, this number would be 2 to the 128 tries. And we've already said that if you want to try something 2 to the 128 times, it's not finishing before the universe ends. So with a big enough output space, finding a collision is extremely hard. You'd have to try 2 to the 128 times, or if the output was 512 bits, you'd have to try 2 to the 256 times, and the universe is going to melt down before you finish trying that many times.